Okay, so this week we're gonna explain two projects. So the project 3 is based on the continuity of a function, and we're gonna do the contour plot. And project 4 will be covered next class on Friday, and that is about spring oscillation. Since spring oscillation is mainly about differentials and differentiability of single variable function, I think I'm not going to cover the content of single variable function that much. So instead, I'm just jump into the project part, and then from next week, we're gonna cover the differentiability of two or more variable function. So we spent time to talk about the early part, so I will jump into the contour plot. So what is the contour plot? So this is the example of two-dimensional contour plot. So it's a contour plot for two variable function. So what does it draw is a curve of a point. Curve consists of a point where value of functions are equal. So all the points on single curve has the same function value. So here, it's not necessarily maybe this is the all contour of a single level, but if you pick up different levels, for example, if you pick up, let's say, value 0.5, so when you collect all the points that has a value 0.5 of this formula, and then you draw the contour here, connecting all the points nearby, and that's your contour plot. So it's something like a section of a 3D graph when you cut that 3D two-dimensional surface by plane, which is horizontal to XY plane at the height of that level. So that's the contour plot. So how are we going to draw the contour plot? So here's a brief explanation of each step. So I'm going to explain first and then show it by drawing it on my pad. So first, you need to divide a domain of your plot, of your two-dimensional function, into smaller domain. For example, let's say if you have a rectangular domain, subdivided into smaller rectangular regions. And then, now, the way you can divide the region is by selecting lattice points, like a mesh grid. Then what you need to do is finding all the lines, which is the boundary of each subregions. So for each line, the boundary line, there are 2 points, 2 endpoints. Let's say they are P and Q. So you want to find whether there is a point on this PQ line which has the value of the function equals to the level that you want to draw. So let's say I want to draw the level of C. So I want to draw the contour plot where the function value is equals to C. So I want to find whether there is a point on the line segment PQ whose function value is equals to C. So what I need to do is checking whether this value is less than 0, and then if that is true, then find the point, or actually that's not finding, it's approximate the point whose function value is equals to C by setting up this equation. So my coordinate of R, which is same as coordinate of position vector from origin to the point R, is given by this linear combination of two vectors with t values here, where t is given by this. So, and then you connect all the points. So here are a brief, rough picture of how contour graph is drawn. So let's say I divided my entire region into 4 rectangular pieces. By dividing each intervals of x and y axis by 2 subintervals, right? The 2 times 2 is 4. So on each region, you have 4 sides, right? And each side, you have 2 endpoints. So at each two endpoints, you compute the value of function. And then you compare with the value of c. So you check the inequality just shown before. Then if that is less than 0, then you approximate the point right here with the linear combination here. And then once you've done that, you connect all the points. So how you connect the point is for each subregion, you have 4 sides, and you find the point which approximates the value, approximately whose value is equals to c. Then if you have these 2 points on this region, you connect the line of these 2 points. And you do the same thing for other regions. So in this region, so the blue lines you see here is the actual contour curve of a function that's not given. The formula is not given here, but let's say this is the contour plot of a two variable function, and you can see that it actually intersects the boundary here and here and here and here. But don't look at the points as an entire region, but look at the points on each subregion. In this subregion, there are 2 boundary points, which intersects with the contour graph here. So you connect these 2 points by line, and you do the same thing for here and here and here. So it's a rough picture of a contour plot. So in actually it's a curve, but if you use 4 subdivisions, then you can approximate this contour curve by this foregone, right? So if you subdivide your interval and subdivide the regions into more pieces, then you can get a polygon with a lot more vertices, and you get a better approximation of the curve. So I think the rest of is the code. So let me give a picture. Let me explain this by drawing the situation again here. Okay. So I think I should sit down here to draw. So here is my region, the entire region. So here, let's say this is x-axis and this is y-axis. And my x range from A to B, y range from C to D. Okay, so let's say I subdivide this region into 4 pieces. So this is the domain, the rectangular domain of function. So let's say f is from A, B, C, D to R. So basically it's a 2 variable function with single real value as an output. So it's a real value two variable function. Now let's suppose my contour curve looks like this. Okay, so if I just do the same thing I did just explained, then here are 4 intersections. So in each subdivisions, I connect 2 points on the boundary. So this is my approximation of a contour curve. But what if I take another subdivision here? So here, now let's erase. Oh, yes, okay. So erase this, and then let's see. So now I have to find 16 subdivisions. And for each subdivisions, I look up the intersection between boundary line and the curve. So here are the boundary lines. So here are actually the intersection of boundary lines. And then you connect all these points. So for each subregion, for example, if you look at this one, there are two boundary lines that are intersecting with the contour plot, contour curve. So you have a curve, we have a line connecting these two boundary points. And do the same thing for other points, other region. So you get this, and here, and here, and here, and here. You see, even though you just increase the number of subdivision by twice, and even though it's only 16 subdivision, you can see that the polygon that approximates the contour graph is way better than before. It's getting better and better. It's actually getting exponentially better. So assuming that you subdivided your region into, let's say, 2 to the power of something, 16, something like that, that's not too big considering the computation speed, but then you immediately get the nice figure of your curve. Although if you zoom in each part, it's just connecting 2 points by line, so it's basically a polygon with lots of vertices, but it still gives a good graph, approximates actual curve, so it's going to be your contour plot. So that's basically how we do it. So, well, let's think about the three-dimensional case before we actually do it, implemented in the Python. So in the three-dimensional case, so we have three variable function, x, y, z. And let's say the value is represented at w. We cannot draw its graph in four-dimensional. I mean, we can imagine there is a four-dimensional space and there is somehow some object in four-dimensional space, which is given as a graph of this function. However, we cannot draw a four-dimensional space. So the only way we can visualize this graph, graph of function, is using contour surface. So what is the contour surface? So I'm going to use LC. Well, it's for level surface, and L stands for level, and C is the level, actual level. So it is given by collection of all the three-dimensional points. So it's actually a subset of three-dimensional space, whose value of function equals to that level. Okay, so we have a good example of level surface. For example, if you have x squared, f of x equals to x squared plus y squared plus z squared, and you want to draw level 1 of that function, that's the sphere. It's a unit sphere, with meaning that the radius is 1 with the center origin. So this is all the collection of all the three-dimensional points satisfying this equation, right? So again, so now there are ways to parameterize the surface, the surface of unit sphere, but we're not going to use that coordination. Instead, we're going to design a way to draw this level surface for any type of three-dimensional, three-variable function. So ideas are the same. So if you want to draw in a two-dimensional plane, you need to subdivide this two-dimensional region. So if you want to draw in a three-dimensional space, you have to divide this three-dimensional region. So we have three-dimensional region that we want to visualize. So we are going to assume that our level surface sits inside of this three-dimensional region. So you don't want to make this region too big or too small. If it's too big, then your surface, level surface, are tiny and almost looks like a point. And if it's too small, then the level surface is actually outside of this rectangular box, so we don't get any figure. So if it's there, then you want to show by which point represent the level surface. So we're not going to like compute all the points because there are infinitely many. Instead, we also subdivide it into smaller pieces. So how do you subdivide three-dimensional region? You divide by subdividing each interval on x, y, z axis. So here I'm subdividing x, y, z intervals into two subdivisions. So there we have 8 regions here. And let's take out one, let's say here, box here. So this is a small subregion here. And if you can imagine, there's a surface passing through this region, right? So let's say I have a surface that passes through this way. Okay? So let me mark the intersection here. So there's a three-dimensional surface passing through this three-dimensional cube, and there is an intersection at the boundary. What we want is to approximate this surface by connecting the boundary points. We cannot draw actual surface without actually showing the boundary. So we're going to connect, let's see, which color is, let's use this color. Connect these boundary points like these. And then if you look at, if you assume that this box, the cube is small enough, then this curve will actually look like a straight line. So you cannot tell the difference by looking at the screen. So this actually looks as if it's a surface if you combine all the cube here with the lines here. So actually you don't see the boundary of a cube. You only see these green lines, right? And how do you connect the lines here? How do you connect 2 points? So for each cube, you look at the boundary surface, which is the plane here, okay, planar surface. And then for each surface, how many are there? There are 6, right? There are 6 surfaces. And for each surface of the cube, you look at 4 sides of this rectangular surface. And for each side, you do the same thing as you did for the contour, two-dimensional contours curve. So you pick up 2 points that connects the boundary line and then computes the value of function and then compare it with the level C and then check out the inequality and then you approximate the intersection point using the linear combination of position vector and then you do it for all 4 sides, and once you get this, what you do is you connect all the points on these 4 sides. So now, since we're using this four-gon or 4 rectangular cube or rectangular region, what happens is if it only has 2 points, then you only need 1 lines, like here and here. But this one, like in this side, you have 3 intersections, 3 boundary points intersecting the surface. So in that case, it's a little bit tricky, but it's hard to find whether you have to connect these 3 points this way or that way or the other way. So it's hard to figure out which direction the surface are actually moving. So in this case, what's best is just connect all the pair of points on the boundary. So then that's going to be your surface. So that's our basic idea. I'll tell you how to improve this further by further subdividing this each rectangular box. Actually, it's better to use the triangle instead of four-gon because of this situation can happen. So that's our ideas. So before we implement this, is there any questions? Oh, by the way, I explained this yet. So why do we have the inequality, such inequality? So let me explain this. So here, so this is two-dimensional or three-dimensional, whatever you want to imagine. There is P and Q, which is the boundary of a line segment, which is the boundary of a two-dimensional region or three-dimensional cube. And what we do is I want to find where my R is so that the value of function is almost equals to level C. So this happens only when Fp and Fq are surrounding the level value C. So if Fp and Fq both are less than C, then we cannot expect that something in between P and Q has the function value C, because it's easy to assume that all the values in between P and Q are less than C. And same thing for when Fp and Fq are bigger than C. Maybe we can safely assume that all the points between P and Q has the value of F bigger than C. So it's only when this Fp is less than F of Q and in between there are C, or the opposite. So this happens, let me erase this for now. This only happens when Fp minus C, Fq minus C less than 0. Okay, so that's why we have to check this one first. So once we have this situation, now we have to find out how much should I move my point P to the direction of PQ vector so that I get the value approximately equals to C. So I need the ratio. I need the inner ratio between PR and RQ. Let's say the ratio of PR is T and the length of PR and the ratio between the length of PR and RQ is T minus T to the 1 minus T. Okay, so let me draw the situation here. Here is my T. So when T equals to 0, that means I'm at the P, right? When T equals to 1, that means I'm at the Q, right? So if I move my T from 0 to 1, I can position my point R from P to Q linearly. And then I know that Fp is somewhere here. So it doesn't matter if P is less than or bigger than Fq because you can, the formula doesn't actually change. But here, let's assume that this Fp is less than Fq. So I want to draw the graph of function value in terms of T. So here I'm assuming my Ft is given by F of P plus, P plus T times PQ, right? So in this case, when T equals to 0, I only at P, and when T equals to 1, then it means actually this, you can assume that this is OP. So OP plus PQ, which means OQ. So we are actually at the Q. So actual function may be not a linear function. Let's say this is the actual function, graph of actual function. So if you think about this as a y, then this is f of t equals to y graph. I want to approximate where my c is. Actually, c is here, but I don't know the function. I mean, if I know all the functions, then there's no need to graph it. But I don't need that exact point. So what I will do is approximate the actual graph of function large f as if it's a linear function connecting these 2 points, assuming that when t equals to 0, the value is fp, and when t equals to 1, the value is fq. So in this case, if I assume that my function is linear, as in the yellow line here, the value of function c will happen right here. Okay, so this is actual, and this is approximation. But since we are using a small line segment, remember we are using the small line segment. So this difference will get smaller and smaller as we shrink the size of each subdivisions. So we're going to take this one as my point R. And how do you get that? So here, let me write more. So we want to know, so this is my t, so this is my t, and this is my 1 minus t. So if I want to get the value c, then this graph is y equals to, let's see, fq minus fp. So since this is a linear line, so the yellow one, so it's better to change the color to yellow. So let me put it in yellow. So this yellow line is y equals to fq minus fp t plus fp, right? Because the x range is from 0 to 1 and y range from fp to fq. So I want that to be equals to c in order to find what actually t is. So t is equals to fq minus fp c minus fp. That's my t. Okay, that's where I should move my point P in order to get to R. So R is now P plus this T, PQ. So you can plug in this T here, right here. Okay? So that's what I'm going to do. So before we implement it in the code, is there any questions? Julian, do you have a question? Is it clear? Is everything clear? Okay. So, how about here? Nayeon, Kim Nayeon. Do you have a question? No? Okay, so let's do it here. So I want to show you how to make a class. The reason why I'm making a class is we're going to use it later when we discussed about the gradient. So I want to reuse it next time. So here is how you define a class. So okay, so we are going to use so the name will be, so you can make the same algorithm for, you can make a single class that works for two-dimensional contour plot or three-dimensional contour surface, but it's hard to think about the algorithm. So let's make it into separate class. So we're going to make a class that is used for making contour curve. So basically, this is how the class look like. let's see, plot. So pass means that do nothing. Okay, so I'm putting the pass temporarily because I just want to show the structure of a class. So once I define class like this, then the way I can use this is, let's see, close this. Takes a little bit of time. So here I can create a class of contour 2D by doing this. And then when I define my class, I can use a function defined within the class as if it's a method of this class object. So C is a class object, and this class of contour 2D. And contour 2D has the plot method. It's a function only for this class. So I can call C plot, and it does whatever defined in this class function. Okay, and the function like this is called the method actually. So you can actually make a class. So it doesn't do anything. So here, cell. Okay. So it doesn't do anything, but you can make your any project. For example, if you're doing what is the first one, the CAPTCHA, then you can make a CAPTCHA program as a class or CAPTCHA object as a class. Okay, so first, this init function, it's not a function or method. It's actually a method, type of a method, but it's a underlying method, default, defined default. And whenever you call to define this object, this function is called. And this is a function that takes an input that is put it into the creation of the object. So now you have to imagine how you're going to use this, how we're going to impose the user to use this class. So I want, whenever the contour 2D object is created, I want the user to input the necessary information about what to draw. Okay, so in order to draw a contour plot, you need the information about the function, you need the information about the region that you want to draw your contour plot, and the better the situation is, you also want the subdivisions that you want to make it into the contour plot. So let's put the information here. So function, and let's say number of subdivision. So function, this is a function, actually it's a two-dimensional function. So function and also the range of the x and y axis. So let's see, x range and y range. Okay, so you can change whatever you want. So the input argument can be any way you want. So I'm just improvise whatever comes into my mind. I'm not actually following whatever is in the slide, but if you can simply copy paste what's in the slide to see that it actually works. So once I have this as an input, you can make that happen, or you can try to implement an algorithm right here, but it's not a good way to start. Simply, if these inputs are called when the class is created, you want to save it. You want to store the information into the class so that you can use it later. So I want to save all the functions. or information function, number of subdivisions, range, and y range into the variable that this class have. So I use the self.func to create a func variable only for this class. Okay, so self means myself, the object itself. And then the same thing for other class. You can change the name of this field, but I just use the same because it's a simple. And then once you did that, when you call the plot method, then you can take the information out from this variable stored in the class. So whenever you put information, it's an input. When you create a contour to the object, that information can be restored in the other object, in the other method. So for example, let's do this. So our func is lambda, let's see, this one. That's a z square, x square plus y square. And let's say number of subdivision, 100 is too much. Let's see, I want to use, let's see, 2. So I only want to divide each subinterval into 2 subdivisions. And x range and y range can be given by the tuple, but I like interval. I like the list, and actually I like NumPy array anyway. So it doesn't have to be a NumPy array, but let me use NumPy array. Okay, so if I use the NumPy, then I have to import. Okay, so when I create contour 2D, I want to put all this information with the right order. So y range. Okay. Plot. Okay. So at this moment, nothing is done because you just created the class object, and this init function is run as it happened up to here. So all the information you put it as an input is stored as an inner variable, self-func, self-num-sub, and self-x-range and y-range. And now when you try to call the plot method of this class, then now you can use this information. So let's try to put some information in plot method. So what do you need to do first? So so you have to organize your code so that reader can know what's going on. So first step is to subdivide the domain. The domain is now two-dimensional domain, two-dimensional region. You want to subdivide. So the way you can subdivide is the mesh grid. So since we have a range, so let's see, xx and yy. Well, first of all, let's see. X is NumPy linspace of self x range and y range, number of subdivisions plus 1. So first I need to subdivide my intervals, x intervals and y intervals, with the same number of subdivisions, which is inputted in the creation of this class. So if I decided to subdivide it into 2 subintervals, I need 3 boundary points, including the starting point and end points. That's why I have to add 1 as a number of this point. And then once I have this linspace, then I can create a mesh grid, xx and yy. I don't need this one. Okay, so that's the subdivision of domain. And what's the next step? So next step is you have to iterate over all the sub-region, okay? So far you only got the coordinate of the lattice point, which subdivides the region. Now we want to actually iterate over all the subregions. Okay, so iterate over each subregion. So you need, well, let's say you need for loop here, okay? And then what you need to do inside of for, the iteration is for each subregion, what do you need to do is look out each boundary. Over each boundary, boundary lines. And what do you need to do for each boundary lines? You want to see if there could be an intersection with the line and the contour line, right? So find if there is an intersection between contour curve and the line. And what do you do when there is such intersection? You find its coordinate. You locate that coordinate by approximating as a linear line, right? If there is, then approximate the point by linear approximation. Okay. So, and then, okay, so for each region, you do it for each boundary line, and you're done with each subregion. Okay, so now what do you do after you're done? So you found all the possible intersection on 4 boundary lines on one subregion. You need to connect those boundary lines, right? Connect all boundary lines. So the way you can connect is not actually doing anything, but you just indicate that these 2 points should be connected, or at least these 2 points should be drawn as the line has to be drawn connecting these 2 points. That's all. So meaning that store the information of line. Okay, so that's all. Once you've done all the storing information, which line should be drawn, then that's all. You can finish this you can finish by actually create a plot, or you can finish it here so that you can store the information in somewhere in the inner variable, and then you can actually plot the contour plot outside of this class. So let's do that way. So once we are done, so what we are doing here, what we want to do is I want to save it here. So in the graph variable, I want to store all the information about the lines that should be connected as a contour, as a approximation of contour plot. Okay, so first question, how do you iterate over all the subregion? So I'll give you time to think about how to start from beginning. So think about how to iterate over the subregion. And then we can discuss the next step. So obviously we need an iteration loop. So for whatever, while is not a good one. for loop is necessary, but now for omni range is from over the list or over the list of numbers. So you need to figure out how to index your subregions as numbers.
주셔서 이름표를
저기 앞에 상자에 있어요. 지금 가져가세요. Okay, I'm going to ask if you have any ideas. So first, is there any group have an idea how to iterate over the subregion? Or any person have any idea? Okay, so I'm going to ask each person here. So, okay, so we have, let's see, I'm not gonna draw. The simplest subdivision here. So let's say I have 0, 1, 0, 1. Okay. Just, it's an X range and Y range. Doesn't really matter. This is not 0. So I want to iterate over these 4 subregions. Okay. Cheney, how would you like to iterate these 4 subregions? So you need certain rule to walk through all the 4 different regions here, right? So if you want to walk through these 4 different regions, what's the easiest way to do it? Yunseok. going around this way, like this one. Okay, so if I need to locate these subregions, how would you number it? How would you indicate these subregions in the program? What's the index of this subregion? 3? Okay, so you want to number it 3. Which one is 1 or 0? Which one is 0?
Maybe 2.
This one is 2? Okay, so which one is 0? Which one is start? We want to number it. Okay, so which one is the first number? You said 3 here. Where is 2 then?
I think maybe there's 0 and 0. Right
0?
is 1.
1, 2. You want to iterate here, and it's this way. So you want to go this way. Okay. So what if you have? Okay, so I want to have a rule that applies for any number of subdivisions. So what if you have this number of subdivisions? What's your rule? How does your rule generalize? Then how do you iterate over these subdivisions? Where do you start? Where do you start?
Maybe started left bottom.
Here, this is 0, and then where do you go next?
Right side.
Right? Okay, so it's 1, 2, 3, and then where do you go? 4 here? Okay, so where do you go up? Keep up, 6, 7? You want to go spiral? That's what you want? Okay, well, that's possible. Okay, that's possible. That's one way you can iterate over an entire region, because you always get a square, right? I mean, also you get if you subdivide it into even number of sub intervals for each side of the two-dimensional region, then you always can iterate entire subregions. Okay, so now it's time to think about how you implement that into the code. Okay, how do you make this iteration? Well, how do you implement this path? Okay, because if I have, let's see, if I see the 14th region, I need to know the coordinate of this region, or at least I need to know, I should know where my region is at. Okay. Okay. So that's the question, the next question you should ask. Okay, so any other ideas about iteration? How you can iterate over? Xiang, you have any idea? No? Any? Yes.
Maybe 1, 2, 3 and 11.
11, 4. Okay, so you want to go this way. Okay, so why do you change the path?
Because we can use it like function, because number 4 can be, we can get by
So you're increasing one y-axis, one step of y-axis, y coordinate. So every time you're done with increasing the x or coordinate, you increase the y coordinate one step forward, and then do it over until you get to the final y coordinate. Yeah, that's actually more consistent, right? So then you don't have to think about what's my y-axis, y coordinate, and x coordinate. So okay, so let's do this way. I want to iterate over So in this case, the outer iteration should be iterating over y coordinate. Okay, so within the y coordinate, you want to iterate over x coordinate. Okay, so y, let's see, for I in the range of subinterval, I want to iterate over the range of subinterval. So this I is the index for y coordinate, and here j is the index for x coordinate. Okay, so let's move it one step further. So I get a double loop here. So what do you do next? For each subinterval, subregion, so now I have a subregion. What are the boundaries of subregion? It's the x and y coordinates. So my x coordinate, so the left bottom corner of the subregion is, should I change to, let's see, let me use other than x and y. So boundary, let's see this way. So the boundary is now, there are 4 boundaries of this region. Let me use this. So I'm using a nested list here. So the first boundary point is xi and yi, sorry, xi, y, sorry, I is for y, sorry, x. That's confusing, so let me change it to j and I, because I like this way. It will confuse me all the time. Actually, it doesn't matter. So if I change it to I or j or I, it doesn't matter. So this is my it's the first left bottom coordinate of my region, right? So I and j also range through 0 to 2, but 2 is not included. So if I have a number of 2 as number of subdivision, then I and j both range from 0 and 1. Okay, so even though I have 3 points, the last point is not covered because I only look at 0 and 1. So here I have xi, yj, and the next point is xi, yj, xi plus 1, yj, and the next one is xi plus 1, j plus 1, and the next one is xi and yj plus 1. Okay, so there are 4 points, 4 coordinates for 4 boundary points. Okay. Okay, so I need to iterate over these boundary points, but I also need to iterate over the pair of boundary points. So far what we have done is showing you this picture. So here we have subregion, coordinate as, so this is ij boundary. So here I have xi, yj, xi plus 1, yj, and xi plus 1, yj plus 1, and this is xi, yj plus 1, right? So I decided that way, so going in the counterclockwise. Then I need to iterate over each side. So when I took this side, that's going to be the pair of these 2 points, right? And I go this one side, I have pair of these 2 points, and then do the same thing for all the other pairs. So I need to do that. So basically, I need to iterate over k in, so how many sides are there? 4. So I need just iterate over 4. So the line is now boundary points, k's boundary points, and k plus 1 boundary points. But the question is, if I get to k goes to 3, then k plus 1 is now 4, which is out of the list of my boundary point list. So I cannot use this. So I forgot s here. So I need to go back to the index 0 by taking the remainder when divided by 4. So that way I get pair of next points, right? So this is boundary line. Boundary line. And okay, at each boundary line, what do? You check whether there is the point intersecting between the curve, the contour curve. So there is one thing that I forgot. The most important thing is the level. Sorry, the level is forgotten here. So I need to put the level information. So this is my level that I want to create as a contour plot. And so boundary line is this. Let's see. I'm going a little bit long way because I already explained in my pad using lots of symbols. I don't want to, create a new symbol to confuse you. So I'm going to stick with the symbol I used in the pad. So P is going to be the one of the boundary line I just created. And Q is the next boundary point on the boundary line. And then I'm going to compute the value of a function at P, and I'm going to store that as a FP. So put it here, and then FQ is the value of function, put it here, and C will be my level value. And what should I look at? I should look at FP minus C times FP minus FQ minus C is less than 0. If it's not the case, then we can skip it. And only when this is happening, we should look for the intersection. So actually this goes, okay, so it's better to have this here. And then, oh, sorry, this is not the grammar, Python grammar. Okay. And then what did I tell you to do? So first, you find T. So what's the formula of T? Here's our formula. So C minus FP divided by FQ minus FP. That's my T. And my intersection is going to be this. Okay. So for X and Y coordinate, I take the inner ratio between FP and FQ, and then I make a new coordinate, X and Y coordinate, according to the ratio. You can use the numpy instead if you want. So that's my intersection. And what do you think? What do you do next? So I want to record that intersection point. So here, let's see. I need the place where intersection points I need to place where I should store all the information about the intersection. So that's my intersection, and I'm going to append this intersection here. Okay. Okay, so once this iteration is over, okay, maybe this should go here. Okay. When this iteration is over, I ran through all the boundary lines and I found all the intersection at each boundary line and I stored it in the intersection points. So there should be one intersection point, right? So if the curves goes into a region, then it should come out at some point, unless it's a boundary region. But anyway, if there is a two or more intersection points, then I need to connect line between every pair of these intersection points, right? So what I should do next is, so if I have number of intersection as num_int, then I range through, so I need to use other symbols. Don't use I because I already used I. So II and JJ. So if you need to go through all the pairs, this is the simplest way you can do it. So simply range from 0 to the number less than 1. And then next index JJ runs through the 1 plus the index II to the end. So then you get all the different pairs of points. So then you want to store the information here. So you append, let's see, intersection point II and yes, intersection points JJ points. Okay. So here, what I'm appending to the graph, the self graph, is that I put the list of lists. So intersection point is already a list. It's a list of two real numbers representing x and y coordinate, and I list them up as another list, and I append that as a entry of the graph variable. So graph is already a list, but I'm taking a list of list of list. So at the beginning, I need to initialize the graph variable as a empty list, and then as I iterate over all the subregions, I append this entry, list of list, as an entry of the graph. Okay? So that's all. That's basically everything. Once I stored all the information into the graph variable, when this function is done, then the line information that I should draw as a graph is stored in the graph variable of this class. Now let's test out whether it works fine. So let's see. I have x, y, and then I have numpy array. I have number of subdivision 2, and also I need a level 1. So I need to put the level as the last value here. And when I plot, nothing happens because here there's no output. There's no plot, everything, nothing. So Omni stores the information, Omni updates the information of the graph variable of the class. So once I run the plot method, I need to look for what's inside of the graph. For each line, Oh, then I need to import the matplotlib because I need to draw. So for each line in the graph in class C, so graph is again list. It's a list of something. Now what's in the list? It's a line. So line is the list of points, right? Okay. So I need to plot the point connecting line 0 and Q, line 1. So when you plot the line, you first list the x coordinates and then list the y coordinate, and that's all, right? So every time doesn't work at the beginning. So let's see. Contour to the, oh, did I? Okay, so let's run this once because you have to store the information about the class. Okay, so now we have figure. And that's a good figure because that's what we're expecting because we already have this. We mentioned that we defined our number of subdivision as 2. That's what we're expecting here. So let's increase it to 4. So then you can now imagine there is 16 subregions without the boundaries are hidden here. But you can see that there are, lines connecting all the boundary points in each subregion. So you get the how many gons here. So whatever gon. So if you increase the number, let's say 8, now you already start to see that it's almost look like a graph, curve. And if you don't like this colorful lines, I don't like this. So then you can color it as black. So now you actually see it looks like a curve. Well, the reason why it looks like a ellipse is that it's not scaled the same. So I'm going to put an option x is equal. Oh, I should put x is equal at the end. Okay, so that's how you now you can see actual circle here. Let's see. Let's choose different function. So what was the function before? So np sine of what? X squared plus np cosine y. So let's try that out. Maybe level 1 is not good. So because that level 1 mostly not happen. So about 0.5. 0.5 not happen. So maybe 0.2. Oh, maybe the size is too small. So maybe let's put 5 to 5. 5 to 5. Yeah, you can see something here. Let's say put 0.5. Okay. The reason why you can see this sharp corner in the polygon is that you don't use much the number of subdivisions. So let's use it like 32. 32 is enough. Yeah. Now you can see the similar figure that I showed in the slide. So 32 in 32, how many subdivisions are there? 32 square. So it's like 1,000 subregions. So you can see that there are tiny subregions, rectangular subregions inside to figure out which line should be drawn in each subregions. Okay. So that's basically how you draw the two-dimensional curve. Now the next step is to draw three-dimensional space. Draw it in a three-dimensional space. I think we have time. So, but I want to understand every step that we just gone through. So if you have any question, ask right now. So you can, if you missed some part of the code, then you can go to our Notion site, and there's a link to this page here on the lecture 8. I just saved it so you can see the actual code on the website. So let's try the same thing with the 3D surface. So I'm going to define contour 3D. So what do you need to draw the contour, a three-dimensional contour surface? Basically, you need similar, but you need one more information about Z range, right? So that's basically it. And if you add Z range, everything now is same. So I want to plot. So it's going to be a little bit long if I don't use it, if I don't separate it into smaller pieces, then it's going to be long. So I'm going to use this way. So first, let's see. I'll do the same thing here, X, or Y, and Z here, and I'm going to mesh grid this three-dimensional region into smaller regions. And then I need to iterate over all the sub three-dimensional regions, right? So iterate over I. So now I'm going to set I is the index for X coordinate, and same thing for J and K. And now if I have I, J, K pair as an index, then that's the index for my three-dimensional subregion. Okay, so I want to define a new function which splits me which gives me the boundary points if there is any. So I'm going to so here boundary points. No. Bound. What's the best way? So I'm going to define a function lines for I, J, K. Oh, by the way, so this is not. Oh, actually, I don't need x, and y, and z. Did I use any x, and y, and z? I didn't use it, right? So I actually didn't require this. I didn't have to. So all I need is I need to save my information of the subdivisions of x and y coordinate because I'm going to use it in a different function called lines. So line means that I'm going to try find all the lines connecting boundary points in I, J, Kth subregion. So that way I can make it a little bit simpler code. So once I find all the lines, I'm going to, actually it's not an append. Is it expand if I need to concatenate two lists? I think it's up. Sorry, so I need to test out because I forgot. So I think it's expand. And let me test out here. So it's not expand. Is it append? It's not append. Forgot. Oh, I can just plus. Oh, okay. Oh, okay. That's easy. All right. So, uh, right. So I'm going to add all the lines to the graph. That's all. So I'm going to do that. So once I've done this, let's see. I'm going to define my function as the sphere, and then let's see. X range is 0, 1, 0, 1, 0, 1. Number of subdivisions and level is 1, and plot. Then I'm going to import. Then I'm going to draw. Maybe 32 is too much. I'll use 16. Then K and plot X is equal. Then I get the figure. So for now, it doesn't work because I don't implement the line function here. But that's basically how the code look like. So that's basically it. Now, let's add one more definition, a function of definition. Definition here, def lines self. So the reason I put self is to use all the variable that's stored in this object. So without self, then I cannot use this self x and self y and self z. Okay. Now the situation is a little bit complicated. Since we are looking at the cube, we have 6 sides. I need to look up each side and then look at the boundary point. So, okay, you can do it by brute force. So, so I want to look at all the 6 sides. Let's see. What's gonna be the best way of doing this? So I don't want to get confused. I want to show you the somehow not a very efficient way of doing this. So I'm going to find the boundary points on, oh, not this. Okay. So what's gonna be the best way of doing this? So so let me explain first, and then before I show you to you. Because if I don't explain it, then you might get confused. So here we have a cube. So here is my xi, yj, k, zk point. This is my coordinate. What I want is this surface for the first. I mean, the order doesn't matter. But if I want this, then what are the coordinates here? So this coordinate is really doesn't matter if it's the matter of which axes are which. So let's say this is x plus 1, yj, and k, zk. Okay, and how about this one? let's say this is xi, yj plus 1, and zk. Okay, and how about this one? So this is xi plus 1, yj plus 1, and zk, right? So if I want one side of this cube, then I need to pick two coordinates, x, y, or y, z, or x, z, and then I need to increase one from the index of those coordinates. So here I picked x and y, and I increased the index of x and y by 1 here, and then both 1 here to get the four corner of this side. And if you want a different point, then you can do the same way. But anyway, this is how you have to iterate over. So if you want to, so now if you want to look at this one, the backside here, then the problem is you have to now move to the direction of z coordinate. So all the coordinates are same, but the different, all x and y coordinate are the same, but z coordinate has to be shifted by increasing the index of z by 1. So this is now, for example, is xi plus 1, yj plus 1, and zk plus 1. Okay, so you can get the same figure here. So right, so it's actually, you can do it for 6 times if you want. It's a little bit complicated. So I don't know how to write this in an easy way, so intuitive way. So what I did in the code here is, if you, let me just look at here. Let me just explain what I did in the code, so you can then try to do the same thing here. So in the code, I put the offs here. So it's a offset of the index of x, y, and z coordinate. So here, looking at let's look at this one. So these are offsets of x, y, z coordinates starting from z 0, 0, 0. So it means that you're looking at xi, yj, and zk here, and then the next point, you move your index of x coordinate by 1, then index of x and y coordinate by 1 each, and then you move back to the index of y increased by 1, and then this last one is only for the sake of the circular boundary here, circular point. So just copying the same offsets in the first. So you do the same thing here, but here you have how many? 6 lists of offsets of the index. So then whenever you have I, J, K region, then you can add these offsets to find out all the sides, all the boundary points of the sides. So then you can iterate over this. So I'm going to use this in the code. I hope that this auto completes for me. So let's see. So offset. So if I write few of this, then I think it will auto complete for me. So 1, 1, 0, 0, 1, 0, 0, 0, 0. Oh, there's a list of this. The list of this. Okay, so it doesn't auto completes yet. Let's see. Okay, so it, not really. Okay, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 0, 0. Then 1, 1, 1, 1, 0, and 0, 1, 0, 0, 1, 1, and 1, 1, 1, and 0, and two more. 0, 1, 0. Okay, now we got it. So we get think 0, 0, 1, 1, 0, 1, 1, 1, 1. Okay. So that's the entire offsets. Okay. So yeah, that's my offset. I can actually find the offset outside of this class, but I did it inside anyway. So for each I, now I have to iterate over offsets. Since I know the here ijk, so ijk here. So what are the boundary points? So boundary points are iterating. So I cannot use this I because I have ijk here. So and then iterate over range of 5, range of 4. So I'm going to append self xi. So this is my x coordinate, the basic x coordinate, but I'm going to add my offsets, II offsets 0, and then my y coordinate will be this, and z coordinate will be this. Okay, 1, 2, 3. I think I forget closing this. Okay. Here I have this. So you can see that I'm not changing the value of x. I'm keep using the x lin space and y lin space and z lin space. I'm changing the index. So I'm changing index from ijk by adding offsets. I defined already here. So that's the boundary point on one side. So I update my boundary points, and once I did it, I simply do the same thing. So I can just copy paste from above. So once I have a boundary point, and now I need to find the intersection point. So it's copy paste here. So all the intersection points are stored in here. So for each, yes. So here I need to indent back to one step here. So I cannot use k. Let's use kk instead. So and then here boundary points k, boundary points k plus 1. Actually, this is range of 4. So yeah, that's fine. I don't need to divide by 4 in here in this case, because I already used this 5 figures. Actually, I need to pick like 5. So I need to range from 5 because I already have 5 points counting back to the original. So I don't need to use divide here. So boundary lines here, and then points, and then I use the same t. Now the intersection point is a 3-dimensional point, so I need to use one more point. So P2 plus T times Q, and then add the point, the intersection point. So here, once I iterate over all the four sides of each boundary surface of the cube, then I have a list of intersection points. All I need to is iterate over the pair of the intersection point and save it to the graph. So I do the same thing here, just add it to the graph. So here. So by the way, so we separated our function into two pieces. So this function, the method lines, only outputs the line information. So and then I'm going to store that line information to the graph later. So once I have these, then I'm going to save it to the lines, section point, and then return it lines. Okay. So once I return that lines, it's gonna be stored in the graph, and then it iterates over all the subdivisions, subregions, so it's done. So basically, plot is the main function, but the actual computation happens in line function. So I'm not sure whether it's gonna work well, but let's try. Let's see. Let's try it anyway. Okay, so I need to run this code once. Okay, and then let's run this. Okay, so oh, by the way, okay, so I just copy paste. I need 3 inputs because we have a three variable function. So, sorry, so it's 2, P2. So let's see. No attribute graph. Okay, so I think I didn't initialize the graph. Okay, so let's put self graph initialized, or it's better to put it in init function so that anyway it updates here. Okay, so and then let's see how it works. Okay, we need to draw as a 3-dimensional curve, so I need to plot as a 3-dimensional curve. Oh, I forgot to put the z-axis, sorry. P2, Q2, and black. So now you can see, this 3-dimensional curve. It's a kind of a meshed. So let me change it to little -1 to 1. Then you get this kind of picture. So you have a sphere as a contour plot. Let me change to another situation. Let's see, we have 3, 3, 3. So it's gonna be a little bit weird function. So you can see it's not a, well, look, it's not good looking. So let me change it to a little bit bigger view. So instead of 1, I get 0 to 3. Then, what's it not? Oh, maybe it's because of 1. So maybe 2 is better. 0.5. I want to show you the figure of this weird function. It's not a sphere. How about use 25? Not drawing properly here. It's a figure of something weird, not weird, but some surface popping up certain part of the surface as a sphere-like shape. So you can test out with that other type of functions here. So anyway, it works. So this is how you can draw this contour plot or contour surface. So this is not a, as I said, best way of doing this because it's there are lots of redundancy, and if you're doing who's doing the contour plot project? Raise your hand if you're doing contour plot. I know that there's one group doing contour plot anyway. Who's doing contour plot? Silver? Where's Silver? Silver group. Not a group 3, section 3? Silver group. Where, yes, you're doing contour plot, right? Okay, so when you're doing contour plot, your task is to increase the efficiency of the computation. So this requires lots of computation. And also, it only uses the square. The problem is sometimes you get too many intersections, so you don't know which points to connect really. So it's so instead of the rectangle, you can use the triangular subdivisions for each region, and then you can draw the similar picture here. And also try to make a code more efficiently so that you can have a better performance of the of this program. So it's fast enough, but it's not fast enough when you increase the number of subdivisions. And I think this is not the best way of doing it. I think something is missing. There's some line missing here. So anyway, that's your task if you're doing the contour plot. And time is up. So next time we're gonna talk about the spring oscillation. So we're gonna basically do similar drawing, but in two-dimensional drawing. So next, okay. So before I finish, I need to mention that we're gonna have a pre-presentation on Friday, next Friday. Okay. So make sure you upload your work on the Notion. Doesn't have to be complete. Just upload what you're going to do as a plan. Okay. See you tomorrow. See you on Friday.